students. We are studying the modeling of step voltage regulator. We have started in the last lecture, and in the last lecture we have seen why we need to regulate the voltage within the limit of say plus minus 10% or plus minus 5% depending upon standard, whichever standard you are following. Then in the last class we have seen various techniques which we can use to control the voltages over a distribution system. So we have seen we can use on-load tap changer with transformer, we can use step voltage regulator, we can use voltage booster, induction regulator, or fixed and switch capacitor. And out of these we are seeing step voltage regulators. We have seen single phase step voltage regulators in the last class, and we have divided this single phase voltage regulator in type A type regulator and type B regulators. Basically construction of them is similar, only the connections are different. So here I have shown voltage step regulator, which is basically B type of regulator. I will show you how A type look afterwards. So in this case, as I discussed in the last class, we need to connect this regulator basically in auto transformer fashions. So since there is auto transformer, there will be one winding which is series winding, another which is winding which is called as common winding or shunt winding, and then there will be for changing the tap position, we will be having this tap connection here, and for that we are using this reactor switching because we do not want to interrupt the current whenever we are changing the tap. So whenever one tap is connected to the tap position, another then only we can disconnect another tap. So basically for that we need this reactor here, which will be basically used while switching or you can say whenever you are changing the tap positions. So whenever one tap is connected to the next position, then only other tap will get disconnected from position. So current continuity will not get disturbed. And we have seen that depending upon your position of this reversing switch, so there will be R switch where actually we can use if you want to raise the voltage beyond this one, beyond normal voltage, and then L we can put this reversing switch on L position if you want to decrease your voltages. And then this CT is actually connected on load side to measure the load current which is getting delivered to the load, and then there will be voltage transformer which will again use to measure the voltage on the secondary side of the regulator. Similar to this, there will be A type regulator which was seen. If you see them, they are just mirror images of each other. In this case the tappings will be provided on low voltage side, and in this case tappings will provided on source side, and basically this configuration is widely used. And in the last class we have seen the operation also of A type as well as B type of regulator, and what we have seen depending upon your position of your this reversing switch R or L, we have seen various configurations. So in this case when your switch is on R position, then the current will flow like this. So IS will go and then IS will come from this side, and then it will get added to your I1. So in this case if you see, this dot is towards your L point. So this is your L here, this is common SL I can say, this is your source, and you can see that your dot is at L point, because if you see here it is this connection is going to L here. So this is nothing but your L terminal only. So dot is towards N, and for common winding dot is here. So if this current is your current IS and this current is current IL, and this voltage is load voltage which is basically VL, and this voltage is source voltage Vs. In this case current direction in the common winding will be decided by dot. So since IS current is coming towards dot, this current has to go away from the dot. So therefore, the direction of current I1 will be like this. And last class we have derived the relations also. We have seen that your voltage Vs is given by 1 minus N2 by N1 into your VL, and this 1 minus N2 by N1 we call it as a AR, which is basically transformation ratio of this one. Similarly, current relations we have got Is is equal to 1 divided by N2 minus N1 into IL. So, basically in this case your Is will be equal to 1 divided by AR into your IL. And then we compare this with respect to our standard ABCD parameter, that is Vs is equal to A VL plus B into IL, and Is will be equal to C into VL plus D into your IL. So, if you compare this equation 1 and equation 2 with respect to this equation 3 and equation 4, we have got your A parameter, which is basically AR. So, AR in this case it is 1 minus N2 by N1, and your B parameter is 0 because there is no term in equation number 1 which is equal to IL. Then the C parameter is unkey 0 because in equation number 2 we are not having term which is related to VL, and your D parameter will be 1 upon AR. So, this is actually parameter when your B type regulator is in raise position. So, here if you want to raise the voltages, your dots will be something like this. So, dots will be towards L terminal, both the dots will be at the L terminal. Opposite of this, when your switch is connected to L position, your current path will be something like this. So, in this case current will be coming like this through this winding regulator winding, it will go to terminal L. Okay. So, if you see this dot, basically this dot will appear here, which is basically at terminal S. So, if this is your terminal S, this is L, then this is common SL I can say. So, dot in this case dot is towards terminal S. So, I can put this dot here, and this dot of common winding at the same position. So, in this case your Is current is coming somewhere here, this is your current IL, this voltage is Vs voltage, this voltage is VL, and in this case also we have derived, in this case the current directions will be something like this. In this case current is going away from dot inside the winding, so it should towards the dot inside the winding. So, current direction will be something like this. So, I1 current will be something like this. So, in this case we have derived your Vs is actually equal to 1 plus N2 by N1 into VL, which is equal to Vs into AR. In this case AR is having plus sign here, into VL. Similarly, we have got Is, which is equal to 1 divided by 1 plus N2 by N1 into your IL. So, in this case it will be Is will be equal to 1 divided by AR into your IL. So, in this case if you see ABCD parameters, so A parameter will be again AR, but AR is in this case is 1 plus N2 by N1. Your B parameter will be again 0 because there is no term which is related to IL into equation number, say this is 1 and this is 2. So, equation number 1 we are not having term which is related to IL, which will make B is equal to 0. C will be also equal to 0 because in equation number 2 we are not having term related to VL, and your D parameter for this will be equal to 1 upon AR. So, you can see that for B type of regulator we are basically getting this equation. So, basically what we are getting AR is equal to 1 minus N2 by N1, where it is on raise position, and we are getting AR is equal to 1 plus N2 by N1, which is for the lower. So, basically I can say it AR will be equal to 1 minus plus, because I want to write it for raise first, and it will be N2 by N1. So, this relation is for your B type of regulator. A type regulator, your signs will get opposite. So, in case of A type regulator, 1 plus minus N2 plus N2 by N1, otherwise it will be same. Now, as I explained in the last class, this relation between N2 and N1 is actually decided by your tap position, and total number of turns in regulating winding we have seen, we need around 10% turns in regulating winding. So, for example, if you consider the turns N1 will be say 1600, I am giving you example, it is not a exact one, depending upon design they may change. Then in regulating winding, the turns will be 160, because we know only a 10% variation in regulating winding. So, the turns will be 10% turns will be in the regulating winding, maximum turns. And if there are say 16 tap plus 16 and minus 16, total 32 taps. So, for 32 taps there will be plus taps which are 16 and minus 16 taps. So, the divisions which you are making, the 160 by 16. So, per tap will be having 10 turns. Per tap will be having 10 turns. So, if your regulator is on normal tap, it will be your N2 number of turns, N2 will be equal to 0. When it is on plus 1, that is in raise position, you need to add N2 is equal to 10 turns. 1 tap change means 10 turns will need to be added in regulating winding, then you will get particular change. So, for 1 tap you are having 10 turns, for second tap it will be again 10 turns. So, N2 in that case will be 20 turns in the regulating winding. So, it will be nothing but 10 into your tap position, which is 2. For plus 3 tap, your N2 turns will be 30, which is basically 10 into again your tap position in this case. So, I can just write it will be 1 minus plus, in this case 10 multiplied by your tap position divided by primary turns are say 1600, which you assumed here. So, in this case if you observe, it will be 1 minus plus into 0.00625. This 10 divided by 1600 will be 0.00625 into your tap position. So, for if there are 16 plus and 16 minus tap, means there are total 32 taps in your regulating winding, your N2 by N1 ratio will be 0.00625 into tap. This configuration is only possible for this one. If there are plus 8 and minus 8 taps, means there will be total 16 taps. In that case, it will be 0.0, it is double of this, it will be 125 into your tap position. So, this configuration I have taken 0.00625, it is possible if there are 32 taps into the your regulating winding. So, this is how we can calculate your AR for any type of your regulator. So, AR will be nothing but 1 minus plus into 0.00625 into tap, and as I told you, this is only possible if there are 32 taps into your system. Now, line drop compensator circuit. Yesterday I have just given brief introduction about line drop compensator circuit. As I told you, it is basically used to control the regulator tap positions, and these regulator tap positions are controlled based on voltage at end of the feeder or wherever location which you want to control the voltage. So, in this case, say this is your feeder and you are interested to control the voltages at the far end of the feeder, and then say to control the voltage of this particular bus, you are connecting regulator here, and then here actually the voltage which is given. And to control the whole regulator positions, we use this line drop compensator circuit, and as I explained in the last class, line drop compensator circuit is basically taking the feedback from your current transformer and then your potential transformer, which is connected here, and this is your line drop compensator. And we have seen that then it is connected to the voltage relay. I am writing it as VR. Then it is connected to the time delay circuit, because we do not want frequent operation of your regulator, and then it is connected to the motor operating circuit, motor operating mechanism. Now, let us see how this line drop compensator works. So, for that I will just draw the inside view of line drop compensator circuits. So, if you see inside the line drop compensator circuit, it will be having this current transformer. Across this current transformer, some impedance will be connected, and then there will be one transformer which is having ratio 1:1. So, you are having this transformer which is having ratio 1:1, and then you are having this voltage transformer here, and then this signal is actually connected to your voltage relay circuit. So, basically this signal is coming from your voltage transformer. So, this is your PT potential transformer, this is your CT, and then current which is flowing through this is say I, and impedance of this feeder is RL is the resistance of this feeder, and XL say your reactance of the feeder. And then the CT ratio says CTP is primary rating of CT, and CTS say your secondary rating of the CT, and the turns ratio of PT will be say NPT. We want to regulate the voltage at this feeder at say 240 volt level. I am just considering LT feeder, single phase feeder say. I want to keep this voltage say 240 volts. However, we cannot exactly put 240 volt, always you need to specify some range. So, say range of the voltage is say 242 to 238. So, variation allowed is 4 volts. So, I can just keep this voltage within this particular limit. Now, whenever current is flowing through this feeder, suppose this regulator is not there, and if the regulator is not there and the voltage at this end say 240, then without regulator will be 240, and there will be some drop here. So, in that case voltage here will get dropped say to say 236. So, in this case what will happen is in this line drop compensator circuit we want to simulate whatever drop which is happening. So, in this case the 4 volt drop is happening, and because of that your voltage is not getting regulated at 240 volts, or you can say from it should be above, always about 238. So, we need to simulate this drop, or we need to model this drop whatever happening along this feeder inside your line drop compensator circuit, and that is why we are putting this impedance here, which is I am calling it as RC and XC, and that should be proportional to your line drop. So, whatever drop which is happening across your RC plus JXC should be proportional to your drop which is happening across your feeder. So, it should actually simulate or model the actual feeder inside your line drop compensator circuit. So, in that case what will happen if there is say 236 volt here and suppose 240 volt here. So, NPT ratio is 1:2 say. So, say here if this voltage is 240, because of the ratio is 2, NPT is equal to 2, then voltage at the secondary of PT will be 120 volt. So, here it will be 120 volt, and the current direction here is like this, means inside CT the current direction will be like this, and it will create drop along this one. So, this drop will be just opposite of this voltage here. So, because of that what will happen is, suppose some current is flowing and here we are getting some kind of say 3 volts drop because of this this voltage here. So, in that case the voltage across your relay is 117 and the set voltage corresponding to this. So, set voltage here is 240, means set voltage we need here across voltage relay which should be 120 volt, and bandwidth is then 121 to 190, corresponding to this I have taken by considering NPT ratio is equal to 2. So, set value of voltage inside your line compensator circuit is 120 volt, which is corresponding to 240 volts, and corresponding to 240 volt maximum voltage allowed is 121 and minimum voltage allowed is 119. But you can see that this voltage is going below 119. In that case this VR voltage relay will get operated, it will give signal to time delay circuit. After some time delay your motor operating mechanism will operate and it will change the tap such that the voltage at this bus will get raised such that we will get again 240 volts at this position. So, this is how your line drop compensator circuit work. Now, question is how to get these impedance values. So, as I told you, this impedance inside your line drop compensator, that is nothing but your RC plus JXC, is basically need to be proportional to your RL XL. So, how to get these values we can just see. For that what we can do, we will just see what are the base quantities in the various circuits. So, there are 2 circuits, one is actually line circuit which is basically transmission line or distribution line circuit, another circuit is compensator. So, circuit which is inside compensator I am calling compensator circuit. Let us say how much voltage we are getting. So, line voltage is actually nothing but your VLN, line to neutral voltage. Basically here we will get this line to neutral voltage across the PT primary coil or at the output of your regulator, and inside the compensator we will get voltage which is equal to VLN divided by your NPT. So, this voltage will get dropped or step down to your potential transformer ratio level. So, inside compensator your base voltage will be VLN divided by NPT. Then base current. So, current in the line circuit is nothing but CT primary, whatever CT primary rating is there, it is actually base current for primary circuit, and then base current for secondary circuit will be just CTS because it is rating of secondary side of the this CT which is inside your compensator circuit. And if you calculate Z base, Z impedance base, so in this case impedance base will be VLN divided by CTP, and in this case it will be VLN divided by NPT, and it should be divided by CTS. So, CTS also will come down. So, it will be multiplied by this one. So, for compensator circuit your base impedance will be VLN divided by NPT into CTS. Now, let us see how we can get the values of this RC plus JXC. Now, if you consider the per unit values of RC plus JXC and per unit value of RL plus JXL should be equal, because I want actually them to be proportional. So, if we are considering particular bases inside line circuits and compensator circuit, and if you calculate per unit values of this and per unit values of this, it should come equal, because they are, if they are proportional and if you are considering particular base quantities in particular circuit, the per unit values should be equal. So, what will be the per unit value in your primary circuit. So, per unit value will be primary circuit will be compensator circuit will be RC plus JXC divided by your base value. So, base value we are getting VLN, and this denominator will go off, it will be CTS multiplied by NPT. So, this is actually base value per unit value in compensator circuit. So, this is actually compensator per unit value, and then line per unit value can be calculated like this. So, it will be RL plus JXL divided by its base value, which is basically this, which is VLN, and this denominator will go off, which is basically CTP. So, this is actually per unit value of line impedance, and this is per unit value of compensator impedance. So, those should be equal. So, on the next slide I will just take them. So, in this case we have got RC plus JXC divided by VLN into CTS into your NPT, which is equal to RL plus JXL divided by your VLN multiplied by your CT primary ratio. So, in this case this VLN will get cancelled out, and if you get RC plus JXC will be equal to RL plus JXL multiplied by your CT primary divided by CT secondary multiply your NPT in ohms. So, basically we are, as I told you, we are interested in getting these compensator parameter which are RC plus JXC. This is nothing but you can get RC plus JXC, it is called as compensator setting, because these are RC and this XC, they will be variable. So, depending upon your impedance of your feeder, you need to set these values. So, depending upon impedance of your feeder, we need to set the values of RC and XC such that these voltage at this bus will get regulated. So, basically what it is doing, it is simulating the drop proportional to drop which is actually happening in the line. Proportional drop will be getting created here, and that drop is getting created here, and this drop is getting subtracted from this secondary voltage of the PT, and depending upon this difference voltage is getting applied across the voltage relay. So, that should be in the range, as I mentioned for this particular problem, as I mentioned, if it is set value is 120 and bandwidth generally defined for compensator circuit, if the bandwidth is say for 2 volt, that is voltage variation allowed is 2 volt here. So, this is your bandwidth for your compensator circuit, and if the voltage across this voltage relay getting beyond this 121 and below 119, the relay will operate, otherwise it will keep on it will not operate. Many times so voltage across, or you can calculate this voltage drop. So, voltage drop, as I told you, so V drop will be equal to this impedance multiplied by your secondary current. So, it will be just RC plus JXC multiplied by your current CTS, which is basically flowing in the secondary side of this one. So, this current multiplied by this impedance, same drop will come here, and since this is 1:1 transformer, this drop will appear here. So, this drop which is happening across this drawing I am calling V drop will be equal to RC plus JXC multiplied by your CTS, and then we have seen that CTS we have got it here in terms of RL plus JXL into your CTP CTS multiplied by NPT multiplied by this CTS, I am just writing as it is. So, in this case the CTs will get cancelled out. So, RL plus JXL multiplied by CT primary ratio divided by your turns ratio, it will give the drop across this one. So, depending upon this drop which is happening here, which will be, as I told you, this drop is actually proportional to your drop, proportional to your impedance of this particular feeder. So, that drop we are considering it here. So, depending upon current in the CT primary, the drop will change. So, as the CT primary current changes, this drop will change. So, this is how your line drop compensator work. So, we have seen till now single phase regulator. Let us go for 3 phase regulator. So, 3 phase regulator, first we will see simple configuration, that is Y connected regulator. So, the Y connected regulator, in this case also, as I told you, generally B type of regulators are used. So, I am just taking your B type regulator which are connecting in. So, it will be having 2 windings. So, this is say phase A, one winding is this basically winding is regulating winding, and then one winding is your common winding or series shunt winding. Then similarly I can plot another phase, it will also having 2 windings, and then there will be third phase. So, this is regulating winding and this is your shunt or common winding. So, this is your phase B and this is your phase C, and as I told you, we are taking this terminal out which is between common winding and series winding. This will become your small a, then this I am taking out, this will become small b, and this if I take it out, this will become small c. And then currents, this current is IA, this current is IB, this current is IC, and this current will be I small a, I small b, and I small c. In this case, since I am considering a raised position, we have seen that in case of raised position, your dot position will be something like this. Dots are coming at loaded, both the dots are coming at the load terminal end. So, dots will be something like this. So, when this IA direction is something like this, so here also it is towards dot. So, current should leave from this dot. This B is also towards, IB is towards dot. So, this also leads the dots, leave the dot. So, this also IC is towards dot. So, here the current should leave the dot. So, current direction will be something like this. So, in this case we can easily write the equation for the primary side and secondary side voltages of this voltage regulator. So, I can just write VAN, VBN and VCN 3 voltages, just like 3 single phase regulators. So, AR, 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 and this will be V small a n. So, here I assume that actually your this is grounded, neutral is grounded, so that is why. So, in this case you can see that there are 3 regulators which are single phase regulator which are connected. So, I just taken the equations which you have derived for single phase. So, for first phase your VAN voltage will depend on AR multiplied by VAN, VB1 will be AR multiplied by VBN, VCN will be equal to AR multiplied by VCN. Now, here there are 2 possibilities. If this regulator is completely 3 phase regulator and there is possibility it will be gang operated, means all the taps of all the 3 phases, if they are operating simultaneously, then your all the 3 coefficient of this particular matrix they will be same. And sometimes what they do, 3 single phase regulators they connect in star fashion, and in that case the control circuit of 3 different regulator works differently. Means there is possibility that 3 regulators will be having or working at different tap positions. So, in that case you need to consider that. So, this AR A will depend on your tap position of regulator A, this AR B which will depend on tap regulator of B and tap regulator of C. So, specifically if you have to mention it, if your regulator is not what is called as gang operated. Similarly, I can write current relationships. So, current relationship in this case, your current IA, current IB and current IC capital will be equal to, in this case again similar to 3 single phase regulators connected in star fashion and star is grounded. So, independently they operate it, it will be 1 divided by ARA 0 0, B will be just depend upon your IB current. So, ARB 0 and C will depend upon your just IC current. So, in this case it will be IA, IB and IC, 3 current. Okay. So, this equation I will just write it like this. So, it will be V line to neutral voltages all the 3 phases is equal to this matrix I am calling AR Y matrix because it is Y connected transformer, and then this is your again line to neutral voltages of secondary side small abc, and this I can write I capital ABC. Again this matrix I can just another name AR current related, so I can just ARI multiplied by I ABC. And this, if you compare this equation with respect to the equation which we have seen, so we have seen that VLN ABC is equal to your A parameter into VLN small abc plus B parameter into I ABC. And another equation which you have seen, I capital ABC will be equal to your C parameter matrix VLN small abc plus your D matrix into I ABC. Now, if you can compare this 1 and 2 and 3 and 4. So, if you compare 1 with 3, so your A parameter will be equal to your ARY matrix and B parameter will be equal to 0 matrix of 3 by 3 size, and your C parameter will be again zeros matrix because there is no term related to VLN in equation. If you compare 3, 2 and 4, in equation number 2 we are not having term related to VLN ABC. So, in that case C also will become 0 of 3 by 3 size and D will be your matrix ARI current related, that is why I am writing I term there ARY. So, these are nothing but your ABCD parameters for this one. Since it is Y connected network, we are getting very simple parameter. So, here all the 3 regulators, they are working independently. So, in the summary of today's lecture, we have seen line drop compensator circuit in detail, and we have seen that line drop compensator circuit is basically required to create the voltage drop which is proportional to drop which is happening across your feeder. So, inside line drop compensator we have seen that there is impedance consisting of R plus Jx, and the voltage drop which is created across this impedance will be used to operate the relay. So, relay will be having voltage relay will be having some kind of bandwidth. If this voltage drop across that voltage relays go beyond the specified bandwidth, your voltage relay will operate. After that, we have gone for modeling of 3-phase voltage regulator, and in 3-phase voltage regulator we have seen Y connected regulator. So, next time we will see delta connected and open delta connected regulator, and we will see some examples on voltage regulator. Thank you.